So my name is Marco Bertoni. I'm professor here at Blekinge Institute of Technology, which is located in the south of Sweden. And I'm professor in mechanical engineering. And today I'm sharing this session on design digitalization approaches. And my relationship with the topic is mostly through what we call here locally, but also more internationally, data-driven design for product service systems. So my speciality is in fact on this notion of product service systems. And also in the past, I've been working in knowledge-based engineering. And that's kind of my synopsis with design digitalization approaches. And if you look at what is a design digitalization approach, today we have quite a variety of contributions. There are design digitalization approaches that address topics related to machine learning. We have papers that are dealing with computer-aided design and coding, and a term that actually I didn't know about before, smell. And I'm curious to know what a smell is in relation to CAD and code. And then sensory functions, we're going to discuss them as well, parametric design, and collaborative modeling. So we are going to have quite an overview of different types of approaches when it comes to digitalized design. And this is in fact quite a big domain. And I think here we have an interesting, portfolio of different contributions that can explain us quite a lot about what digitalization is today. So I think without further ado, we probably can start with the videos. I see, in fact, Sergey joining now. Yeah. Hi, welcome. And just in time, I just said, okay, we can launch the videos. And our moderator, Robert, please, we can be ready. The first presenter today, the first video recording is from Oliver Bleisinger. I hope the pronunciation is right. He's researcher and business area manager automotive at the Fraunhofer Institute for Experimental Software Engineering. And his research is focused on virtual validation in model-based systems engineering via simulation and machine learning approaches. So thank you very much. And please, let's start with the first video.
So, hello together. My name is Oliver Bleisinger, and I will be presenting a short overview regarding our paper, Machine Learning-Based Simulation for Design Space Exploration. So maybe to start with the starting point of our applied research, I would like to motivate how we actually started researching in this field. So why did we say we would like to use machine learning-based simulation? We have here on the left side our system lifecycle, and it is a system lifecycle shown on the top regarding system generation N. And now you can imagine we are trying to develop the system regarding generation N+1. And mainly we are focused on the automotive domain. So as you can imagine, in the automotive domain, there are some special conditions. For example, when you have a system generation N+1, which you are developing, then normally you always have a system generation N. So you're using components, and mostly it's like around 80 to 90% from, let's say, a car you developed beforehand for the new system. And we were actually thinking, how could we be more efficient when we have data from the operational phase of the system generation N to develop the system generation N+1. And one approach we are looking at is the so-called machine learning-based behavior modeling, or let's say machine learning-based simulation for early virtual testing. And then we try to use this technique or this approach to do design space exploration and a specific application example. And when you look at the right side of the slide, you can see especially this early virtual testing in comparison to late virtual testing, where you mainly need simulation models that don't have to have 100% accuracy, but maybe 95% accuracy is good enough to do some design space exploration. So this was our main motivation. And furthermore, we are also thinking about going in the, let's say, field of AI expert systems. So AI-based systems, which may help in these different design steps regarding design space exploration. So this is one of our main motivations. So let me go more in detail regarding the automotive case study we were looking at with our research. So the data was acquired from an automotive supplier, and we used it for our data-based approaches or our machine learning-based simulation. Let's say the challenge was really regarding design space exploration, because we had software. It was a software for an energy management system, or from an energy management system for a hybrid vehicle. And we were looking at the so-called state of charge from the battery system. And we were trying to optimize the state of charge based on different design parameters from the software. So we were mainly focused on the software. One, let's say, main impact regarding using machine learning-based simulation is the speed up, really quite fast speed up of design space exploration, because you have a lot of design alternatives, so a lot of parameters you could set. And we were looking at how do the software parameters have influence on the overall state of charge after simulating a specific load cycle for our hybrid vehicle. So we had different kinds of concepts for this hybrid vehicle regarding the energy management system. And then we checked which kind of state of charge would actually result by this design and by this given load cycle. So actually, one of the main tasks was also modeling these different types of simulation models. And as I said, we did this data-based. And here I would like to describe how we actually did the modeling, or how we actually set which components need to be modeled. And there, of course, there was a special emphasis on the electrical effect chains. So we looked at different electrical components of the hybrid vehicle. And there we tried to do a specific system cut, or cut a specific part of the overall powertrain out of the system, and then try to model the different components. So the components we were looking at were the e-machine. We were also looking at the electrical inverter, and of course at the battery. In respect to these specific components, we were recording measurement data at the supplier and used this to try and model with some neural networks different kinds of simulation models. So it was like kind of neural net-based prediction models. And we put all these components together, as you see on the different types of inputs and outputs of the single models. And then we were able to do this design space exploration with this machine learning-based simulation approach. One main benefit, as I already said, is that you don't need specific domain knowledge to model these different types of simulation models. And you are quite fast, because execution of neural network models, when they are trained, of course, already, is quite fast. And this was one of the main benefits why we said, okay, let's try to use these machine learning-based models for design space exploration. So now I would like to give you a short overview what were actually our main key results regarding the machine learning-based simulation, or the specific neural network models. So we did some kind of training runs, and we variated some different hyperparameterizations for the machine learning models, and looked for the, let's say, overall best models we could find. Of course, we did this somehow systematic. The details are in the paper. And now, as you see on the top, there are the 3 different single component models we were looking at. We have a quite high accuracy dependent on the error measurement you are using. So we were looking at 2 different types of error measurements. So MAPE is actually only the mean average percentage error. And as you see for the feed-forward neural network model for the e-machine, we were around almost 100% accuracy. So let's say maybe 99%. For the inverter model, you can see that the recurrent neural network model, the RNN model, was the most accurate. And maybe you are around 97% accuracy with the RNN model regarding the MAPE error measurement. For the battery model, you can also see in this case for the MAPE 96% accuracy, because the error is only around 4%. Just to give a conclusion, you can say the machine learning-based simulation approach was, in this special application, very efficient, because we had models which were quite accurate, at least for early testing. So there we can say, okay, it is useful to use machine learning-based simulation, because you have like 96% accuracy, and this is enough for design space exploration. And if you would like to have some more details, then feel free to read the paper. Or if you would also like to learn more about machine learning-based simulation in general, then just feel free to contact me.
Thank you very much. And now we move quickly to the second presentation, to the second video. The author of the paper that you see now on screen is Peter Rosso, which is a PhD student at the Design and Manufacturing Futures Lab from the University of Bristol, where he completed his Bachelor in Mechanical Engineering. His research focuses on improving the editability of CAD models by applying refactoring techniques using graph databases. And the paper addresses a concept of technical debt, which is also pretty new to me. So, please.
Good morning, afternoon, and evening, everyone. My name is Peter Rosso, and I'm a PhD student in the Design and Manufacture Futures Lab at the University of Bristol. Does CAD smell like code is a mapping between a violation of computer science and design principles and CAD. My work mainly focuses on creating means to tackle technical debt generated during the creation, modification, and extension of CAD models. CAD and CAM tools have increased their importance and use over time. As modern enterprises have become more common, CAD have become part of this growth, enabling the description of physical objects and artifacts in a digital space where they can be linked with the respective product data or between each other. Because of these connections, there are multiple drawbacks in not reusing these CAD models and leveraging the reusability of the model. This paper proposes a mapping between classification of programming smells and CAD smells. In programming, the term smells refers to the characteristics of code likely to negatively impact quality of code. Considering the properties and behavior of CAD models and the similarity to object-oriented models, we propose the classifications of 19 CAD smells, of which 2 are demonstrated as illustrative examples in the following slides. CAD smells are possibly a symptom of a design-related technical debt. Technical debt is the debt that accrues when you knowingly or unknowingly make the wrong or non-optimal decision. As I mentioned earlier, a series of costs of not being able to reuse CAD can result in technical debt. Some of the reports referenced in our paper highlighted 49% of industries within the report lost between 3 and 4 hours fixing product data. 32% of this organization missed deadlines, and 29% of them ordered the wrong parts. Throughout this paper, we took the top-down approach followed by a bottom-up approach. In the top-down approach, we established a parallelism between object-oriented programming and CAD, and then we used existing classifications because they were based on a more extensive and more available set of data. Then we consider if the classifier program smells apply to CAD, if they're presentable from geometrical modeling systems such as Fusion 360, Inventor, or other programs. And then we thought about what environment are specific to. We had an external review followed by a bottom-up approach in which we defined the smells from a CAD perspective, associated the smells with a CAD-specific examples, and reviewed again our classification. In object-oriented programming versus CAD, in drawing the parallelism, we considered principles of FAME, which are abstraction, modularization, encapsulation, and hierarchy. Principle of abstraction argues that simply for the simplification of entities through reduction and generalization, while in CAD, we can see this when drafters can change the level of abstraction they operate on within from sketches to assemblies. In the principle of modularization, is concerned with the separation of concerns between information and the information hiding. This is possible in CAD because the drafter has the ability to break down any physical object into smaller entities. Then we have the principle of encapsulation, where we create a cohesive and loosely coupled abstraction. This is not as important in CAD as in programming. And there are different levels of information hiding, which some geometrical model systems enforce and some don't. Lastly, we go principle hierarchy, in which we try to enforce hierarchy on organization of abstractions, which either have an is-a or has-a relationship. In CAD, we mostly have a has-a relationship, which is a type of composition relationship. And this is characteristic and necessary to define boundary representation, constructing solid geometry like models such as feature-based, which are the ones we're most familiar with. In our research, we started from 90 programming smells, of which 25 were selected. And among 25, the 25 selected programming smells, 19 were confirmed as possible CAD smells. In the table on the left, you can see the 25 selected programming smells, of which only 19 were confirmed to be CAD smells. For each of the smells, we showed whether they were not were not preventable from a geometrical modeling system, and whether they apply to the sketch part or assembly environment. The first of the two examples we want to show is duplicate abstraction. This may arise when two or more entities have identical type and common properties beside their position in 3D space. As you can see in the example at the bottom of the slide, we have two objects that look the same but have been modeled in different parts. On the right of the slides, you can see the timeline, the construction tree, in which you can see some of the entities, some of the sketches and some of the features could have been condensed using mirroring and building a more condensed form of the model. The second example is broken modularization, in which this may arises when data such as dimension and entities that the drafter should have localized into single entity are separated and spread across multiple abstraction. As you can see, again, we got the same object that we used an example before, but in this case, as you can see in the timeline on the right, the broken modularization creates a lot more sketches and entities, which could have been condensed in a single sketch, in a single extrusion. In both cases, we saw that the starting point for both smells was the same. So sometimes the same object can demonstrate multiple smells. It is important to start with one and see if other exhibit until you have removed all of the possible smells that are affecting the file. In conclusion, in this paper, we presented a mapping between the classification of programming smells and CAD smells. CAD smells are a possible symptom of design-related technical debt. And this is important because identifying the symptoms can help us addressing the problem of technical debt through techniques such as refactoring.
Thank you very much. So it's time for the next video. The next video is from Benjamin Kraus. Benjamin Kraus is research associate at the Institute for Product Development and Machine Elements at the Technical University of Darmstadt. Please, the floor is yours.
So, welcome everybody. My name is Benjamin Kraus, and I'll give you a short presentation on our development method for enabling the utilization of a sensory function in a component within a system based on its physical properties. For the motivation, why did we create this method? Basically, we're right now in the trend of further digitalization within the industry. And for this, we obviously need digital twins, which needs to be fed data, and this data we need to somehow measure out of the system. And there are several questions that arise in this regard, especially how can we actually measure there, what quality are our measurements in the end, and how usable are the measurements for us. What we found here is that the measurement path, so the point, so the length of the path between our point of interest and the actual measurement, the location should be relatively small so that we have less disturbances within this path, and generally leads to better measurement methods. So this leads to so-called close to process or in situ measurements, which are desirable to improve the general data created by those systems. How can you achieve such a function? One idea is here to use sensing machine elements, and one specific subcategory is very interesting, is the sensory utilizable machine elements. Basically what you do here is you introduce a sensory function into your standardized machine element, and for the sensory utilizable ones, basically their physical properties and the sensory function are intertwined, so you use the physical properties of the machine element itself as a sensor. And what we then found is that we can actually also derive this method onto the non-standardized design elements. For an example, to give you a better understanding, I brought here a valve, which is closing body, moves relatively to the housing. And when this happens, you can see if you have a non-coating layer that the capacity between the housing and the body basically follows this line, and you can determine the opening degree with it. Another example is resistive fabric, which we use to determine if it's wet or not. Now I want to give you a very short introduction to CK theory. What does CK theory do? It has a concept space and a knowledge space. That's where the name comes from. And those two spaces interact with each other. Inside the concept space, we have undefined or non-decidable propositions. And what we do is here we refine our process, we structure our process, or so on. The knowledge space, we increase our knowledge or deduce some new knowledge from it. And between those two, we can basically, from K, we can introduce knowledge into our concepts and to further subdivide them. And then in the end, if we found the proper concept, we can put it back into K-space to have our knowledge expanded. How does this work in detail? Basically, as you can see here, left and right, concept and knowledge space. And if you follow down here, the design path, you can see you basically always have interactions between your knowledge and your concept. So sometimes you need to go back to your knowledge and increase your knowledge to further define or refine your concepts and vice versa. So now I want to give you a very short overview on how our development method actually works. It consists of 4 steps, and we're starting with the building structure of the system and our desired target variable. Then we identify potential design elements which we want to use for SUDEs, and with a load path model, then we use those and basically put them into an effects graph and use the effect chains generated by this to select feasible solutions for this. And out of those, we want to then decide which are the most feasible ones or the most interesting ones for us. So what we do now is do a robustness check for those potential SUDEs. And we do this again using effect chains and the effects graph. And after that, after having this pre-selection, we want to do like a ranking fine selection. For this, we have like a more general weighting system developed for the SUDEs, which then leads us to our final ranked solution list of SUDEs. So how does this method work in general? To give you an overview, I want to show you the mechanisms in the CK theory. So we start with the knowledge of our developer and the proposition that it's possible to introduce those functions into our system. Then we expand the knowledge of our developer by the system modeling methods, and then do in the first step, as shown on the right, get the list of the potential SUDEs. Then we move on to the second step. We want to partition our candidates for more feasible, which are feasible. For this, we expand the knowledge again with the state of the art, do a pre-partitioning, and then by using the effects graph, we can basically subdivide those possible design elements and rule out some of them which might not be feasible. Then we head on to our robustness check, and here we can again use the effects graph and the knowledge of our developer together with the disturbance list, which we expand the knowledge of the developer again to do a pre-selection of the principal SUDE solutions. And then we go to our final step, the scoring, and this is done by expanding again our knowledge with the target weighting system and then using that to do a scoring of the final SUDE solutions. So as a summary and conclusion, what did we achieve? We made it possible that with our proposed method, the SUDEs can be found and evaluated. The method includes the usage of multiple different tools, and specifically the target weighting system, which was designed to rate the SUDE candidates. But the method, as you can see, still requires some pre-knowledge, especially in the field of trend analogy. So what we want to do in the future is we first want to simplify the method to decrease the starting hurdle for the user. We want to automate the generation of the robustness check. So this has not to be done manually within the effects graph. And we're also looking at a possible system integration to simplify the candidate selection. And then finally, after we refine it again, we want to do a nice crossover study for the evaluation. So thank you so much for your attention. And if there are any questions, let me know. I'm open. Thanks.
Thank you very much. So I would like to remind everybody here attending this session But you can post your questions in the chat, and we will follow them up with the authors later on at the end of all these presentations. And I already see quite a few questions being posted here. So keep doing that. Thank you very much. So the following contribution is going to challenge my German, in fact, because I'm not really good in German, so I will apologize. I apologize already now for my pronunciation. The following paper is from Benjamin Gerschütz, I hope is correct, who is research assistant at Friedrich Alexander University of Erlangen and Nuremberg, I hope, and is going to deal with enabling design checks of parametric designs using digital engineering methods.
Hello, my name is Benjamin Gerschütz, and I'm research assistant at the FAU Erlangen-Nuremberg. Today, I want to introduce our contribution, enabling initial design checks of parametric designs using digital engineering methods. Let's have a look on a company producing bike parts. This company may have parametric standard parts they work with. And each new design has to go through a product validation done by the simulation department. This iterative process is creating a pool of simulation data, mostly stored in databases. Unfortunately, the simulation experts are rare. Therefore, simulation departments are bottlenecks in most product development processes, since they are involved in every iteration but are often understaffed or inexperienced. On the other side, the available pool of simulation data is growing, and there are several powerful digital engineering methods to use this data automatically and support simulation or design departments. We want to realize the democratization of simulation and enable designers to perform initial design checks in real time on their own. The simulation expert is not replaced in this process, but serves as an expert who provides assistance and performs the final validation. And this first check of the designers is what we want to understand as initial design checks. One drawback of the actual academic methods is that they are encapsulated in individual systems. And embedding in a design process chain is missing. So our vision is a system that provides support for the design process from the design engineer to the simulation specialist. So today we want to focus on the central research question: how can existing simulation data be used to realize reliable and easy to use initial estimates by the design engineer? In our concept, the basis is a pool of simulation data stored in a simulation data management system. In an industrial context, this system contains all simulation performed in the company in the last years. And a product designer who is going to do an adaptation design of a parametric model now only enters the unknown parameter set into the system through a web interface. The SDM now checks if this parameter set exists in the system and presents the result if it's available. In the other case, an automatic estimation of maximum stress and displacement is done based on the stored data using data-driven methods like regression. And based on the model fitness factors like the COP or absolute errors, a result quality check is performed. If no sufficient result is estimated, the system automatically runs an FE simulation. And since most designers are unexperienced in FE evaluations and suffer in evaluation simulations in plausibility, additional support is given in the whole system. The level of simulation plausibility check is based on a neural network which is also trained with the available simulation data pool. And with this, the designer is given a hint if the simulation result is plausible and therefore resilient. And even if the developer isn't confident in evaluating the results on his own, the simulation specialist can use the generated data to perform an expert evaluation without having to run a simulation himself. The application of this system offers many potentials for the product development environment. By estimating new simulations through meta models, iterations for product revisions can be shortened, which leads to time and money savings. Since the designers can perform the initial design checks on their own, bottlenecks can be reduced with the simulation department. And the total number of iterations between simulation and design departments are reduced too, since the quality of the designs going to a final validation is much higher and therefore less iterations are needed. With all the above, the workload in simulation departments is reduced, since no standard tasks have to be performed and the specialists can use more time for critical problems which needs more time. As mentioned, the approach has the potentials for cost savings due to the front loading of testing in earlier stages of the whole process, and the plausibility check supports the generation of more meaningful simulations and increases the total result quality. To conclude, we have shown the potential and the power of data to support designers. We can perform initial design checks for new designs and have shown an integrated FEM process chain with added plausibility check. In the future, we want to focus on testing various prediction possibilities like regression and case-based reasoning, and we want to check if the plausibility checks are possible for the result prediction as well. So thanks for your attention, and I'm looking forward to the discussion.
Thank you very much. So we are approaching the final video, the final presentation of this session. Then we move into question and answers. So the following, the final video is from Sergei Yaps, who is a PhD student in model-based systems engineering and automotive security engineering at Fraunhofer IEM in Germany. Please.
Thank you that you are watching my presentation on collaborative modeling of use and damage scenarios in online workshops using a 3D environment. I'm Sergei Yaps. I'm a research candidate for 3.5 years, and I do systems engineering for 9.5 years. Previously, there were several hacks concerning auto vehicles. So in 2015, security experts showed from home office that they can fully remote control a vehicle. In the end of 2020, security experts showed that they can just project something on the street or on a tree and manipulate a Tesla vehicle so that it reduces its speed or stops even if there is nothing on the street. I want to illustrate my approach, my example based on the road sign assistant. Suppose we want to develop such a road sign assistant, which is today available basically in every middle class car. Of course, we have people which have to create a concept, and the concept development team consists of experts from different fields, which typically lead other people. And the question is, what if I want to consider security at this level? Which input can I get from this concept development team? Which input is already available at this stage? I asked people from LinkedIn, and they said they get requirements, use cases, and a system architecture. the main use case here is we want to have a traffic sign recognition. Based on it, the driver should be warned, and then the speed limitation should be started automatically. Of course, we can document the outcomes of such concept development workshops and security workshops with creating requirements and goals. We can also get more detailed information. And I want to say or illustrate my example based on the video board. So what is if someone shows a traffic sign on a video board so that this triggers the traffic sign recognition from a car? Which damage cases could occur here? One would be cause speed reduction for passing vehicles by displaying a speed sign. For such cases, we developed a tool, 3D Engineer, which uses Unity, and it looks like that. So we have a 3D environment in which we can import every other available environment, which also can be created. And for this tool, we can also import among of thousands, hundreds of thousands, free and free available 3D objects, so that we can express our thoughts to other persons without using specific modeling languages. Here we have this girl which wants to hack the black vehicle. For our case, for our damage scenario regarding the speed sign on the video board, we also tried this. We have one vehicle in the front, one vehicle with a short distance in the back, the yellow one, and the hacker, the girl here, which achieved to show the sign on this video board. And this leads to a crash, because we have a short distance between the two vehicles, and then the display which shows this traffic sign, which was not expected by the vehicle. We tested our tools and developed it over 3 years. We had 14 workshops with different teams, and identified over 100 damage scenarios using it. And the most important part, we also tested it with product development experts and with people from automotive engineering. And basically the main outcome was, so you can just use this tool for brainstorming and then finally to derive a description which will be used in the later stages of engineering. Of course, I tested this. Does it work? Yes, it works. So you can show such a road sign on the street, and this will be detected by standard vehicles. Thank you very much.
Thank you very much to all the contributions and all the presenters. So I have seen quite a lot of activity here in the chat, and I think I will start prioritizing the questions here in the chat, and also I marked down quite a few for all of you. And I believe we can start in the order you have been presenting. And I have seen a few contributions actually in the chat addressing Oliver. In fact, there is one contribution in particular, which is the one from Benjamin Gerschütz, our presenter number 4. Benjamin, do you want to ask your question by yourself to Oliver?
Yep. So thanks, Oliver, for your interesting presentation. I wonder what database you use for your approach, and if you can quantify the time advantage of your shown approach compared to a classical simulation approach.
Then thanks, Benjamin, for the question. So maybe I will take up the first part of your question. So which database we used for the simulation, or the machine learning-based simulation approach. So it was around, I think, 450,000 data points. And we had a frequency we were measuring from 10 kilohertz. So you could say if you know how many data points we have, and you know what, of course, the frequency is of where we really took the measurement data, then of course you can also estimate how long actually the data is going. So it's just a few seconds actually we were capturing, but with a very high frequency. So, but this is for all component models. So we had over 500,000 data points, but for all 3 components. And we also measured some additional data for validation, for example. So maybe this clarifies the first part of your question. And the second one was regarding the, let's say, simulation speed up of the ML-based simulation approach. And we didn't measure it directly because there are actually 2 components, I think. One is related to modeling speed up. So the speed up when you're performing the modeling of the simulation models. And the second part where you save some time is, of course, the execution of the simulation models. And we have a project where we will be also evaluating this in industry. But at the time, of course, of this presentation, we didn't evaluate it until now. But what we did is, for the second part, we had another use case. So where we checked how fast are the simulation models compared to classical models. And there was also a paper published, so also from our institute, also from our department, where we also used this approach, but for a completely different use case. It was the simulation of DRAM, so computer RAM. And there we had a speed up around factor 10. So it was 10 times faster, the simulation models, the neural networks, than the classical simulation. So I hope this helps a little bit or clarifies at least a part of your question, Benjamin.
Oh, thank you.
No problem.
Well, I take the chance, Oliver, to follow up on this question. In fact, I see that you have been presenting, as you write also in your paper, these results from a case study. Do you plan to have more case studies in the future? And what is the range of applications that you see for this approach? Because currently I'm working with validation of sensors for autonomous vehicles. I was wondering if this approach can be helpful there as well.
Yes, so actually we have quite a lot of use cases. So this is just one where we applied it. So where we have very concrete results at the time of the publishing of the abstract for this conference. But we also have a second use case, which is also with an industrial context, which will be presented in, I think, next month, so around in 2 weeks, but at the ProStep IVIP symposium, so also regarding product development topics. And that is actually related more on commercial vehicle and simulating that. I think it was an air cartridge. I don't know the pronunciation correctly, but it was related to another component of a commercial vehicle. So we also have a second use case, and also the results are presented, the data set. Also based, I think, around on 67 vehicles we use to capture the data together with Volvo. So this is also publicly known because of the conference which will take place in 2 weeks. And then we actually, because it said sensors, we actually also have a research project. It's not an industry project, it's a research project where we are trying to use this approach to model so-called soft sensors. So it's a kind of virtual sensors, but in an industry 4.0 context. So we are trying to parametrize simulation models for sensors to do some kind of potential analysis in future with this approach to find out what would be the benefit of applying different sensors in some production scenario, for example. So we have multiple areas where we're doing this. And we're also right now trying to implement more tool support. So we are building up a kind of, let's say, AI expert system to guide through this different steps for this application of the machine learning based simulation in different scenarios or different use cases. And we are also trying to, let's say, put more focus also on the design space exploration. So also visualization of different results. So I hope this helps a little bit, maybe especially the part with the sensor modeling.
Yes, these are many pointers for me to look at. To be honest, it's great to see how many cases and the variety of things we are trying to do in this domain. Thank you very much, Oliver. We are probably coming back to you later. Now we go quickly through all the presenters with some questions, and then we continue coming back to some of you. I see that we have in the chat 2 questions for Peter right now. One is from Lorenzo Giunta. I don't know if Lorenzo has the ability to, have open microphone and ask the question. Otherwise, I will just read the question from the chat. Probably is the fastest way. So Lorenzo is asking you, Peter, have you looked at the CAD smells? Do you believe there is a possibility to eliminate this automatically during the CAD generation process, as is occasionally possible with code? So you probably can see also the question in the chat. So having looked at the CAD smells, do you think this can be eliminated during the CAD generation process or not? I think
Peter is just going to refresh his page.
Yeah, I think
just a second.
Coming in a second, yes.
Sorry about that. Yeah, that worked. You can hear me. Yes. So the question was: have you looked at the CAD smell? Do you believe there is a possibility to eliminate this automatically during CAD generation process? I think there is a possibility, yes, but with current capabilities in terms of like how CAD models are represented and speed, I don't think that would be possible in the same way it's done with code. The reason is that code, when this happens in code, it happens over a text file, because it's just looking at text structure and comparing it to semantic rules that are characteristic of the language or the paradigm that you're trying to design in. For example, object-oriented programming, one example. And the amount of data they has to go through is less, and is and the type of connection are all of an explicit kind. When you refer to a certain data variable, you are referring directly to it within the text. In CAD, there is both an intersection of implicit and explicit connections, and there is a lot more data around it. So it's like, if you are concentrating on this kind of operation, there will be a lot more noise. So either computers will have to go much faster, or we need to represent something in a different representation, which coincidentally is which is also like Michael, when he introduced me, said that I look into graph databases. The idea of using a graph database is that would have a much faster read speed, and we'll be able to consider multiple connections at once and be able to look through the scenarios and change the structure. And if we were to have a graph representation, perhaps it will be possible with current machine capabilities to change the structure of an object as it goes. The second challenge, though, in doing so would be with respect to until you get to a certain complexity of the object, there is no way to tell what is the best alternative. And if you continuously change something for while the person is editing it live, you might confuse them. They might not get any benefit from the structure that you're proposing them, because every time they look back and then try to build on top of something that is supposedly better than what they had, they will need time to get familiar with the new structure. And if this happens multiple times, they will spend more time getting familiar with novel structure rather than improving and adding features to the structure they already built.
Thank you, Peter. I have a question related to this concept of technical debt, because it reminds me another concept, which is monetary cost. I was wondering if you can attach any type of monetary loss to these smells. Is it possible, even theoretically, to quantify from a monetary point of view the loss connected with these smells?
Well, if we look at one of the study that I mentioned in both in the presentation, and it's just cited in the paper, there's two of them. They quantify that was specific for North American industry, but we can probably see this translating to other European and it was like all over the world to like model-based engineering companies. Once you know how many hours a person has to spend in order to fix things, then you can start having a first ballpark in terms of like monetary evaluation of the loss in money and time by accounting what is the average cost that an institution, an industry has for this individual. So if now on top of my mind, I don't have the numbers, but it's like if you were to consider that, so like you just look, how much are we paying average in our country or in average everywhere, engineers, or at least people that have the clearance to access certain data, because sometimes you could say like, oh, this is minor work, but there are also privacy issues. Only certain people can access certain parts.
Yeah, exactly.
And yeah, considering that information should be able to get a monetary evaluation, a ballpark. I would expect it to be higher than that though.
Okay. No, good to know. But in any case, it's kind of possible theoretically. Is it something that is in your very far future, research-wise, or to quantify the loss?
Maybe not research-wise, but maybe professionally. I'm looking into work more on this on my own, in terms of like in this year, in terms of like trying to see if there is. If a tool and methodology can be brought to industry, so a way to show the valid, like the advantages of doing something like this is proposing, is to show numbers and show like what exactly. Actually it's like what. So that's why I already thought about that. I was like, how I would show something like that. There was another question in the
sure, from our moderator Robert.
Yeah,
Robert.
So the question was, how did you identify smells in CAD environment, and have you conducted your research on traditional CAD or collaborative CAD,
Yes.
like Onshape or both? Sorry, yeah. Did you want to add anything to that?
I'm waiting for your answer first.
Okay. So we mostly focused on teaching experience both in Fusion 360 and Autodesk Inventor. Some attention was given to some like programs like CAD Query or that allow or OpenSCAD that allow you to have a scripting language to work with CAD, but the main focus was on Autodesk Inventor and on Fusion 360. In future, and at the moment, we're trying to validate this kind of smells and see if there is even a tighter parallel by looking at how you would programmatically express a conglomerate of feature in OpenSCAD, and look at whether the same detection techniques that you would have to find a smell of what certain kind applies as strictly as we found it in CAD. Using CAD, what we did, we looked at the CAD structure of certain models, and we looked at the graph representation that we give to that model, considering implicit and explicit relationship. I mentioned this earlier, and what I mean that is explicit relationship are the one that you can see on a timeline, on a construction tree, and those are the ones that people usually assume to be the only relationship in. But today we also talk about parametric design, which is what it relies on what we call implicit relationship. You don't see them necessarily, but you are creating more connections. So while we look at our CAD file and think there is a construction tree, is much more alike to be a graph. And if the connection of this graph becomes too dense, you might have problems. You might have a brittle structure. So we started making consideration of this kind and look at how this translates in terms of both hierarchy, modularity, encapsulation, and all the principles that I mentioned earlier. Onshape came into our radar after we did this work, like immediately after, but that is definitely something that would help bridging that analysis that I was mentioning between a comparison between OpenSCAD and Fusion 360 or Inventor, because it would bring in the same environment both the representation, especially because of the feature script functionality that was presented at the beginning of the conference on Monday.
Yeah, I was just curious for the Onshape if you maybe developed some sort of framework or methodology for the analysis of CAD actions within those audit trails which Onshape provides, because I'm doing something similar myself, like analysis of user behavior in CAD environment.
So we use analysis. We're using analysis of user behavior not to, at the moment, not to determine whether there is a CAD smell, because that it would be best to do it when there is a state of the model as static. So when the model is not being edited, just being able to look at the structure and say there is a problem or there is not. But we are using it to compare different versions of the same model. So we are kind of finishing running an experiment in which we designed multiple CAD models in Fusion 360 of the same artifact. So we got the same object and has been represented in different way with different construction trees, a little bit like the one that was in my presentation. And the objective of seeing that is to show that the difference in construction and the difference of the structure of the construction tree do affect the number of errors and the time the user takes to familiarize with the object, and possibly it would have an impact on the cost of further development with specific files. So it's important to take account the structure of the file.
Oh, thank you, Peter.
Okay, thank you.
Thank you, Peter. There is a question instead for Benjamin Kraus about the CK model. Sergey, do you want to pose the question yourself?
Yeah, can you give me an example for the transition from known to unknown? Just a simple one.
A very simple example are, like, for example, design catalogs. So if you have a concept and, for example, you need a transmission to transmit like a torque or something, you can have a log to the design catalog, which is like a quantity for you, and then partition your design. For example, saying, okay, I want to have like a gear transmission, or I just want a simple shaft, or some, so you use your knowledge to refine your concept of a machine or system.
Sorry, Benjamin is hacking a bit. Probably it's not just only with me.
Sorry.
It's
Okay.
hacking the microphone for some reason. Let's try now. Yeah. Can you just? Yeah, I think Benjamin has logged off and is probably coming back pretty soon. But there are more questions, and we probably get back to that question when he's back. There is instead another question for the author of the fourth paper, but I see Benjamin is back.
Okay. So I hope it's not lagging so much.
No, now it's better. Can you just repeat shortly what you said before?
Okay, great. So one simple example, if you want to design a system or a machine, you often have to transfer torque from one place to another, and then you can access the knowledge, for example, in a design catalog where you have the different transmissions, which tell you, okay, I can transfer the torque in a certain way, for example, use a gearbox or so on, and then you can use this to redefine your concept of your actual machine. And what we use in our case here is we want to introduce sensory function to the design element. One example was that valve closing body, and what we basically do is we see, okay, we have a relative movement between the components, and to detect this relative movement, which is interesting for us, what kind of physical effects can we actually use? And one result then, what we then use, we go into our known space of physical effects, which we have in a catalog or we moved it to an effects graph now to make it easier to access. And what we found here, for example, is like if you have like if you basically have a non-conducting layer between the moving components, and the components move relative to each other, it's similar to like a variable capacitor. So it basically changes the capacitance depending on your movement. And in this case, basically what you do is you go from your known space. Okay, we have a capacity, we know it changes, and then we connect it to our system, to our concept, where we had first the abstract concept. Okay, we want to have a valve that which measures its position only based on its own properties, which we couldn't solve yet. So we used the known knowledge to redefine our concept, to then move to a concept which is actually a solution for a problem. I hope that.
Thank you. I understood.
I have a question for you as well, Benjamin. I was wondering, why did you apply CK theory first, and what is your lesson learned? I mean, was it useful to apply CK theory in order to frame a problem? What challenges did you encounter when trying to apply it in a real case? You know, can you share a little bit your experience with CK theory?
Yeah. Okay. So basically, I ran into it like at the beginning of the year on like there was like a tutorial from the Design Society, and I thought it was very charming to actually show how a method works. So I thought CK theory is very nice to show what are actually the steps within a method, where, for example, here in design method, what you're actually doing. So are you introducing new knowledge? Are you basically encouraging the user to expand their own knowledge, and how is the concept refined over the process of the method? So I thought it was very nice to explain a method, how it actually works, like what's the background of the method, how the method works. For using it itself, I think it has the drawback that it can be very abstract, and to really do like the next step in your design process to define, okay, I'm doing this definition, this definition, this definition, you basically get like a sort of hierarchy, which I think is not really always the case. For example, if I design a table, I then in CK theory, I would first say, okay, I want 4 legs, for example, and then would say, okay, I want to make it out of wood. But I think those 2 steps are also interchangeable. I can first decide if I want to make it out of wood or not, and then basically the how many legs I want. So, but like from a methodology standpoint, I think it's really charming just to explain how a method works. Like especially like if you want to like differentiate, for example, between like in the German area very common Paul-and-Bytes method, which goes, you can really see in CK theory, okay, I go do a really wide search first, go really far, and then just select back down, is basically the basic idea of this method. But if you have different methods like parameter analysis, you basically make like a deep guess first. You can make like a intuitive solution, and then you go back actually and say, okay, maybe I want to change this up about it, and go back up the trail. So it can help how to understand how methods work, like from like a knowledge concept interaction.
Thank you, Benjamin. It was a quite illuminating answer for me. I have to check this tutorial you talk about. I haven't gone through any tutorial on CK theory, but I probably need to check on them.
Yeah, I think like the person who does that is the Pascal Lemasson from the Mine in Paris.
Yeah. Exactly. I mean, it's on the Design Society website. But
it's like they have I think they have some stuff about it on it's called the special interest group on design theory.
Okay, that one. Yeah. Perfect. Thank you very much. We move to author number 4, which is named Benjamin as well. And we have a question for you from Oliver. Oliver, do you want to pose the question yourself?
Yes, of course. So thanks, Benjamin, for the presentation. I was actually wondering if you implemented the process which you have shown on slide 5. This was the process steps you were shown. If you implemented this in a specific tool, or if you're working on a kind of, I don't know, maybe it was a kind of AI expert system which is guiding the maybe guy who would like to do some simulation or something. Did you implement it somehow, or are you planning in the future?
Parts of the approach are implemented yet. So we have the similarity search in the simulation data management system. We use ANSYS Minerva for this. And the result estimation and potential re-evaluation is realized in ANSYS OptiSlang with an added web app. So the later user, the designer, can use the whole system by only using a browser and don't need the ANSYS system or OptiSlang system on his own machine. The plausibility check at the moment is standalone in MATLAB, but we plan to integrate this approach into the OptiSlang as well. And at the moment, we are checking which potentials case-based reasoning has for result estimation, since therefore we don't need a huge database, but can start with a small one, which is constantly growing by adding new simulations, but without the need of training the whole meta model every time.
Okay, thank you. Maybe we'll give a short addition to my question. Did you actually also look at TDM systems? So you told something about the SDM system, so the simulation data management. And there's like one project I'm working on where we are combining simulation data and test data. So you can do like a kind of intertwined validation of design. So not only virtual testing, but also physical testing and also the comparison between both. Are you planning maybe in the future? Are you actually also working in this field?
Not by myself, but I have a colleague who is working on just this field. So adding test data back to the design phase and gaining the insights from test.
Okay, thank you. Yeah, maybe I will come up to you offline. Thanks.
Yep.
Okay. Benjamin, I have a question. I actually have 5 questions for you, but I will never have time to ask all of them. But I think I will start from, you talk about democratization of simulation. What do you mean?
Democratization of simulation is the idea to front load some simulation tasks back to the designer. So the designer can do first evaluations, be it a full-size simulation or estimation, and can use the results for himself and not being or without the necessity of asking a simulation engineer, which will cost much time in this industrial practice.
I understand. I have a question, in fact, on the quality check and plausibility check. Is the output some sort of a scalar number, or is it just more like a narrative text, like a judgment, good, bad? I mean, what is the shape of this check?
At the moment, both the quality check as well as the plausibility check are a classification. So it's plausible, it's not plausible, or it's high quality, low quality.
Okay.
We think about making this continuous, so we can say, okay, it's 80% plausible, but at the moment, there are 2 classes for each.
Okay, thank you very much. So I might have some time to come back to you, all of 5 later on, but I would like to address Sergey now. I saw that you mentioned LinkedIn as a data collection source. To what extent did you use LinkedIn in your research?
Okay, yeah. Yeah, it was. Wait a moment. I think that there were two things. So one, I don't remember the stuff which I wrote in the paper. What?
Yeah.
Basically, I just asked. I had a post and asked okay, yeah, I know it again. I posted a picture from my paper concept. It was about tools which you can use for, I don't know, brainstorming or so on collaborative work. And I asked them some questions. Yeah. Okay. And basically I just used it to extend my list. So do you know, basically it's a new tool which I could use regarding this question, and it helped. Yeah.
Yeah, because I mean, this type of field data gatherings activities were quite debate today, because some people say that these tools are very much biased, especially LinkedIn, because it's not a random sample, so you cannot really trust these results. Some others say that some results is better than no results. So what is your position? What do you think about
okay. So you can just start, I have nothing, and can you say something to me? Okay, then it's official, of course, biased. And if in my approach was, I have found something, and now I want to fill the gaps. Did I miss something? This was the question. Okay, of course, it's also biased, but I also had an initial set of tools. Yeah,
it was a kind of a method for triangulation for you. More or less, to verify your primary findings and primary data sets. Okay. And I have, in fact, another question for you, because we are working quite a lot nowadays with a software named Carla. You probably heard about it. It's a 3D environment for these autonomous machines. I was wondering, what is, I mean, you have been applying 3D environments, and quite detailed, I saw from the pictures in your videos. So what is your lesson learned about using these environments with people? I mean, what is the main advantage to really put people in these 3D environments compared to just, presenting something in a PowerPoint? Or can you elaborate a little bit more about that?
Yeah, we had I think over 3 years 14 workshops with first with a lot of students, and then later with project partners and also experts in the field of automotive and automotive security. It was also in the time of Corona, the pandemic. So basically, we had this constraint. We have to work in our research project and we have to create results, but we cannot come together because we are distributed over the whole Germany. So we came up. 2 years before, we had this tool. It only worked on one computer, and we can show you via Microsoft Teams a presentation, and that's it. So, and then we thought, what is the problem? Is here that it's not you cannot collaboratively edit it or add something. And this was the idea. Basically, what is if we extend this tool so that you can just paste the link into a browser like Onshape, and then everyone can enter and everyone can place objects, can say something parallel in Microsoft Teams. I have this idea. I want to create a street. I want to do this and that. And if someone explains something, someone else can simultaneously add something or change something or propose to do something. So the speed increases, but only if the tool is really easy to use. Basically 2-3 minutes introduction, not more. So I would say Onshape is already, for me as a computer scientist, it's good, but it's not. So I would say that the learning curve is still. I need some minutes to understand.
It's still something.
So basically, make it simple so everyone can use it, and make it accessible for everyone, basically with the link. And the benefit is, in the end, you can create a picture and put it in every of your engineering tool, and then you can capture the situation very fast. So you don't have to read a lot of text and understand complex models. You just have a picture. And then you can read the text and analyze the models. So this was, I would say, the main outcome. It's just for brainstorming, just playing around. But in the end, the descriptions and this prototyping and playing around are better than before.
Okay, thank you. We are planning actually an experiment on these 3D environments. That's the reason why I'm asking. I see, unfortunately, that the time, of course, has run out, and also because we have quite a lively discussion. And I thank you. I want to thank very much the presenters, the authors, and the audience here. And I believe now we must leave this session for the marketplace and then for the plenary session at 1:45. And by thanking you all, okay, let's meet around, maybe a social event tonight. Who knows? Bye, everybody. Bye-bye.